Welcome to The Explainer. Today, we are diving into something called logistic regression. And trust me, it sounds complicated, but it's this incredibly powerful tool that helps machines make some of the most critical decisions you can imagine.
I mean, think about it. How does a machine decide if an email is junk, or even more important, if a medical scan shows something dangerous? That's the question we're tackling. We're stepping into the world of classification.
So, you might have heard of linear regression, right? That's for predicting a number, like how much will this house cost? But logistic regression is totally different. It's all about predicting a category. It's not answering how much, it's answering which one. Is it spam or not spam? Did the student pass or did they fail?
But here's the problem. A simple straight line, which is what linear regression uses, can go up and up forever. That's fine if you're predicting house prices, but it just doesn't work when you only have two options, like yes or no, pass or fail. You can't have a prediction of super pass or mega fail, right? A straight line just isn't the right tool for the job.
Okay, so how do we fix this? How do we take that line that goes on forever and turn it into something that can actually make a clear decision for us? Well, the solution is this really clever, kind of beautiful mathematical trick called the sigmoid function. You can just think of it as our probability converter. It takes any number, no matter how big or small, and just squishes it so it fits perfectly between 0 and 1. And what this does visually is pretty cool. It takes that straight line and bends it into this elegant S shape. And now every single point on that curve is a probability. It's no longer just a random number. It's a value between 0, meaning no chance, and 1, meaning definitely yes. And once you have that probability, making the call is super easy. We just draw a line in the sand, usually right at 0.5. If the probability is more than 0.5, we say it's class 1. If it's less, we say it's class 0. Simple as that. All right, so now our model is making decisions. Great. But are they any good? I mean, how do we know if we can trust it? This is where things get really interesting, because just looking at a simple accuracy score can be, and I mean this, dangerously misleading. So let's say we built a model to detect a serious disease, and it comes back 80% accurate. You'd probably think, hey, 80%, that's pretty solid. I mean, it's a B in school, not bad, right? But what is that 80% number actually hiding? Because that one number, it never tells the whole story. And when we're talking about something like a medical diagnosis, the details it's hiding could be the difference between life and death. Okay, this is what's called a confusion matrix. Think of it like the model's detailed report card. And if you look closely, you see a massive problem. See that box for false negatives? It's a 3. That means our pretty good 80% accurate model told 3 sick people that they were totally healthy. That is an absolute disaster. So to really understand what's going on, we need to look at two other numbers, precision and recall. Precision is basically asking, of all the times we predicted someone was sick, how many times were we actually right? But recall, and this is the crucial one for our example, asks, of all the people who were truly sick, how many did we actually find? And you can see why this matters, right? In medical diagnosis, missing someone who's sick, that's a false negative, is way, way worse than flagging a healthy person for a few more tests. So our main goal isn't just generic accuracy, it's to get the highest recall possible. We have to catch every single person with the disease. Okay, so let's say we've tuned our model and the recall is looking great on the data we have. But here's the next big question. Will it work tomorrow on a new patient, on data it has never, ever seen before? This is where we run into the huge problem of overfitting. It's like a student who crams for a test by just memorizing the exact questions and answers. They might ace that one test, but the second you give them a new test on the same topic, they completely fail. Why? Because they never learned the actual concepts. Our model can do the same thing. It memorizes the data instead of learning the patterns.
So obviously, we need to guard against that. We need a solid way to check how our model is really going to do out in the wild when it's faced with brand new data.
And a fantastic way to do this is with something called k-fold cross-validation. It sounds fancy, but the idea is pretty simple. Instead of just splitting our data once into a train and test group, we split it into, say, 5 or 10 chunks, or folds. We then train the model on all but one chunk and test it on the leftover one. Then we do it again, using a different chunk for testing. We repeat this over and over, and then we average all the scores. This gives us a much, much more reliable idea of how the model will actually perform. All right, so we have a way to test for overfitting.
But what if we could build our model to be smarter and fight against overfitting right from the start? That's the final piece of our puzzle. We can do this using a technique called regularization. The best way to think about it is like putting guardrails on the learning process. It basically adds a little penalty every time the model tries to get too complex. This encourages it to ignore the random noise in the data and focus only on the real important patterns that are going to apply to new data too. And there are two main ways to do this. The first is called lasso, or L1. Think of it like a really tough editor. It looks at all the pieces of information the model is using, and if one isn't very helpful, it just cuts it out completely. Its influence becomes zero. The other type, ridge, or L2, is a bit gentler. It doesn't fire any features. It just reduces everyone's influence a little bit, making sure no single feature becomes too powerful. So let's pull all of this together. This is your toolkit for building a great classification model. You've got the sigmoid function to get those probabilities. You've got the confusion matrix to see the real story, not just the accuracy. You've got precision and recall to focus on what actually matters. And then you have these amazing safeguards like cross-validation and regularization to make sure your model is robust and reliable. When you use these together, you're not just building a model, you're building a model you can actually trust. Because ultimately, this all comes down to a really important idea in machine learning. The goal is not just to build a model that's right, but to build one that's right for the right reasons. We need to know it's getting the answer because it truly understands the pattern, not just because it got lucky on the data we gave it. And that really leaves us with one last big question to think about. When a model is making a decision about someone's health or their freedom, how do we as humans decide what's good enough? The tools are getting more and more powerful, but that just means our judgment, our ethics, become more important than ever.